Welcome everyone I know you're all busy with exams and marking and things, but I'm glad you could drag yourselves away for a very interesting seminar from Dr. Paul Rowley, who's here visiting with us for 3 or 4 months from Loughborough University in the UK. Now, some of you who were here, he tells me it was 20 years ago, but that sounds
nearly
extreme.
Alarmingly,
But,
yes.
Paul was here and worked with us when we had the Renewable Energy CRC running, and Paul ran the education program for us and did some really interesting work with educating local governments on energy efficiency and renewable energy and other interesting things that we did at the time. Paul's got a PhD in material science from Cambridge and has been working both in industry and academia for the last 25 years. He actually has worked on coal and nuclear, but then saw the light and has been working
Saw the glow.
the glow with renewable energy more or less since then. He's worked in Canada and the UK, and then had the stint here in Australia, and also worked with BP Solar after he left the university here. He, since 2008, has been running the Multi-Scale Energy Systems Analysis Group, or the MESA group, at CREST in Loughborough University, and he's going to be talking about some of the work they're doing, which is aiming to look at all the complex interactions to make a sustainable and carbon-free energy system. That's what he's going to talk about today.
Thank you, Muriel.
And
thank you for the invitation to present at this seminar. It's a real pleasure for me to be back in Sydney after such a long time away. And it's wonderful to see your new accommodation. When I was last here, we were up the hill slightly in the old electrical and electronic building, which I understand is also due for a major refurbishment very soon. So wonderful to see so much positive change going on here at UNSW. It's always a pleasure to come back, as I said. A few words then about myself, and perhaps to give a bit of background to what I'm going to talk about over the next 45 minutes or so. As Muriel said, by training I'm a material scientist, and I started off many years ago during my industrial placement year in the nuclear industry. Now, in the context of uncertainty and risk, that's obviously a very interesting sector to work in. I worked at Sellafield, which is one of the world's largest nuclear fuel reprocessing plants, still operating. It was also the site of the world's first commercial nuclear reactor, feeding electricity into the local distribution network. It peaked at 300 megawatts at the time and didn't last too long. But if I were to say to you that the current decommissioning cost for that facility is in the order of 140 billion Australian dollars, you'll get a feeling for some of the known unknowns and unknown factors that can have severe implications on the investment landscape for electricity generation, if not health and safety. I was also working at Sellafield when they had a major leak in 1984. Oh gosh, that's so long ago. I was very young. And that closed the beaches in the whole of Cumbria for about 18 months. Some of you may, who are from that part of the world, may even remember that. Following Sellafield, worked in research, specifically for corrosion protection systems, for coal and nuclear thermal plants. Coal at the time was king coal. There were hundreds of thousands of people employed in the UK mining coal. We had and still have some of the biggest coal plants in Europe. For example, if you were to visit Drax, which is a 3.2 gigawatt output coal plant in Yorkshire, probably of a similar scale to some of your large coal plants here. It would be somewhat surprising to the miners of the 1960s and 1970s, upon which the coal fields of Selby are upon which Drax is located. It would be somewhat surprising for those miners who toiled in the ground beneath Drax to find out that today Drax imports coal from Australia, Brazil and Colombia because of the power of global markets and the techno-economics, the economic advantages of mining cheap coal from Australia and transporting it to the UK rather than digging it from deep drift mines. And also with regards coal, it was only in the last few weeks that coal was not part of the UK electricity generation mix for a few brief hours earlier, well, last month actually, during May. For a few brief hours there was no coal generation on the UK mix whatsoever. And for a few days, and this would have been a major surprise to those coal miners I mentioned earlier, for a few days during May, PV output, energy output, not power, PV energy output, outstripped coal for a number of days during May. So things are changing, the landscape is changing, the system is changing, and we must, in order to predict the outcomes and impacts of this new 21st century paradigm that we're entering, be able to manage the uncertainty associated with unpredictable and perhaps more predictable future outcomes. Before I continue, a few words about CREST. CREST is the Centre for Renewable Energy Systems Technology. It's located, no surprise, within Loughborough University. That's where I work. I've been an academic there since 2008, as Muriel said. I worked at BP Solar. I worked at UNSW before joining Loughborough, and I worked in knowledge transfer, industry engagement, short courses, workshops, dealing with the needs of industry primarily with industry prior to becoming an academic in 2008. So the work that I'm going to summarize over the next 45 minutes or so is actually more recently than that. It's work that's been ongoing for the last 3 or 4 years. That's where we are, bang in the middle of England, if not the UK. The geographical centre of the UK is up here. The geographical centre of England is here. Not many of you may have heard of Loughborough. It's near Leicester. Leicester, famous latterly for King Richard III, who was found in a car park in the middle of Leicester following his defeat at the... Now I'm testing myself with my history, but Bosworth Field, thank you, Gavin, where Henry I was victorious, I believe, or was it Henry II? Henry V, oh my God, my history is terrible. If you are a fan of Shakespeare, you'll know a lot more about it than me. Some people say that the finding of Richard III's body in a car park and his subsequent interment at Leicester Cathedral was the primary reason why Leicester City won the Premiership last year. Those of you who are into your soccer, football, you may have been aware of that. But those are the two key famous aspects of Leicester, I'm afraid. It's a rather small town in the middle of England. But that's our campus, supposedly the largest campus, contiguous, whole campus in England, although I've heard other universities have claimed that, have made that claim also, including Nottingham up the road. But let's just assume for the time being it's one of the largest campuses in the UK, famous for its sport. You can see the running track here. The cricket pitch is next door, if I can just get this working, where the England team train. Doesn't do them much good, I'm afraid, but they train there. Rugby, etc. It's famous for its sport science, and its engineering. And we are based in this building here, next to the new science park, and this is the Energy Innovation Building, and we're located here next to Intelligent Energy, a fuel cell company. So there's an energy cluster, both academic research and development and industrial research and development within our building. Okay, now on to the main topic of the seminar. I've borrowed this slide from a very good friend of ours. Tony Ward is head of power and utilities for Ernst & Young in Europe. He's based in Birmingham, down the road from us, and he very kindly contributes to our training and education program, specifically my course in energy system investment and risk. And I'm using Tony's slide here because it gives a much better illustration of the dynamic nature of change that not just the British and the European Union power and energy systems are undergoing, but also illustrative of the transformation that's going on in Australasia as well. So that's the 20th century picture, a picture of centralized, large-scale production of energy. Tony's also got gas here as well because he's head of power and utilities. Of regional trading, local markets, transmission via high voltage systems through the low and medium voltage distribution networks to passive consumers who take what they're given and have no alternative. But the 21st century picture is somewhat like this and very different. It's a mix of large-scale centralized generation, smaller scale centralized generation, large wind farms, increasingly offshore, in northwestern Europe at least, large-scale solar farms, relatively large scale in the UK. Our solar farms are a maximum output of, say, 50 megawatts, which is significant. Who would have thought 20 years ago that we would have 10 gigawatts of solar PV in the UK? It would have been rather ridiculous to think of, but now we have it. We have also, in addition to that, around about 15 gigawatts of wind. Significant proportion offshore, more expensive, more risky, more uncertain, and a more significant proportion onshore. Onshore wind is now the lowest levelized cost of energy of any power generation technology in the UK. Obviously, it depends where it's located. And that lowest levelized cost of energy fact is specific to high wind speed sites in the north of England, Wales and Scotland, which has its own socio-economic uncertainties and aspects which come to bear when considering long-term energy system planning. But I digress. We've got a mix of embedded, distributed, small-scale, larger scale stochastic or intermittent generation. We've got some larger scale, what's called renewable energy generation. Now then, Drax I mentioned previously, a monster of a coal-fired power station. Dorothy Thompson, who's the CEO of Drax, and her board have decided to take what is in some quarters regarded as a very risky decision to spend 2 billion Australian dollars retrofitting currently half of the capacity of Drax to burn wood pellets. Wood pellets that are imported predominantly from the southern states of the United States. About 6 million tonnes a year of wood pellets are imported into the UK solely to be burned in Drax and subsequently in Lynmouth, which is a 1 gigawatt coal-fired power station. This is a strategic decision by the UK government in conjunction with the industry to increase our proportion of renewable energy generation. I'm saying renewables because the embodied carbon associated with that pelletized biomass import is as yet undefined. But we know what the probability distribution might be of the embodied carbon in that. So is it really renewable? Where are the carbon liabilities associated with processing and importing and storing and burning that wood pellet feedstock in the UK? Where is the carbon liability associated with that fuel feedstock? Where does that actually lie? In the United States or in the UK? As yet ill-defined. And that's an important issue to address in the context of Paris. Then as we move towards the consumer, we have a significantly and rapidly changing landscape there. We have this concept of prosumers. Consumers who can take an active role in the way that not only they consume electricity and thermal energy, but also perhaps in the way that they can trade the energy that they generate locally within their communities or on their buildings. And this, if this is to happen, that must be facilitated by the right level of smart technology or intelligent technology. Not just smart metering, which as they're being rolled out in many parts of the world, including Australia and the UK, isn't actually that smart. They're relatively dumb. They're mainly being implemented as a means to facilitate real-time cash flow for the utilities, rather than result in intelligent operation and control of this Internet of Things type structure that seems to be evolving, So what does this mean? What are the key changes and challenges? Obviously, we have to drive towards a low-carbon system in order to meet the imperatives of Paris post COP21, if not the environment at large. This move from centralised to decentralised, new sources of energy production, both large and small, and in terms of the diversity of energy generation. Security of supply is a key issue. I've heard some colleagues who I've worked with in the past and still work with from the DNSPs, as we call them DNOs, or from National Grid, actually referred to embedded stochastic generation as a threat to the security of electricity supply. And from their perspective, that might be a valid viewpoint. Often in political circles, we regard stochastic renewables as a benefit towards security of supply because it's indigenous, homegrown energy. But there are different perspectives, different stakeholder perspectives that need to be taken into account. Funding issues, how we create new business models, how we evaluate the risk associated with those business models and ownership structures in this brave new world. All of this diversity and change, this complexity, all adds to the uncertainty associated with predicting future outcomes. We have a change going on in the UK and the rest of Europe, and I'm sure here as well, with regards the amount of power flow that's happening at the high voltage, the transmission system level. That's reducing, and significant increases in capacity being connected at the low and medium voltage. The distribution network operators will be required to take on some of the roles that are currently being managed, being contracted, some of the services being contracted at the high voltage level, such as with regards local frequency and voltage control services, for example. So the responsibilities of the DNOs will change, and that's an opportunity for them, no doubt. We mentioned smart meters and flexible grids and the need for intelligence with regards power flow and dynamic system operation, and the brave new world of smart meters and the Internet of Things. And finally, as I alluded to before, this aspect around prosumers and active consumers, not just consuming but also trading and generating energy. Now for something completely different. We're going to talk for a few minutes, and I'm mindful of the time. I'm already overrunning, so I will move quicker through the next slides. A few definitions with regards some of the topics we're going to talk about. Donald Rumsfeld, some of you might remember Donald Rumsfeld. He mentioned known unknowns and unknown unknowns. Risk can be regarded as a known unknown. It's the deviation of a future outcome. This is for the purposes of this presentation. Risk and uncertainty can be defined in a number of ways, but for the purposes of our discussion here, risk can be defined as the deviation of an actual outcome or an actual future outcome relative to what we predicted or what we expected that outcome to be. And that can be quantified, for example, in the form of a probability distribution. Uncertainty refers more to the unknown unknowns. It's about the whole realm of possible future outcomes, but it's about an outcome that is difficult or impossible to measure. And this is a definition that I haven't seen improved since Frank Knight's treatise of 1921. An unknown outcome versus a known outcome. Outcomes that can be quantified, perhaps by a probability distribution, against outcomes that we don't have real insight into, and about which we don't have an insight with regards to the underlying distribution. Now, uncertainty in a complex system of systems, because we're dealing with a system of systems here. We're dealing with a technical system of systems within which we have set non-technical subsystems, such as the people that consume and generate energy, for example. Within a business system, within a market system, it's a system of systems of extreme complexity, which the outcomes of which cannot be predicted deterministically by an algorithm such as x equals ny plus z. So uncertainty is key, and its management is key when embarking upon an exercise of integrated modelling. Integrated models can cover, and in terms of the work that we're doing, they do cover a wide variety of domains: socioeconomics, fuel affordability, economics and finance, technical issues, environmental impacts. And the uncertainties inherent for each of those domains, each of the uncertainties inherent in those domains, can arise from a number of different types or sources. And because integrated models are designed to capture a wide range of cause and effect aspects across these domains, these uncertainties accumulate and propagate throughout the type of modelling that we're trying to do. So if one tries and strives to solve these problems deterministically, not only do we not really have the computation, the easy access to the computational resource that's required to solve these ultra-complex deterministic problems, if we do try to do that, but we tend to accumulate and propagate through the modelling the uncertainty associated with each specific aspect. Now, we talk in our work a lot about taxonomies, typologies, classification systems, because we do deal a lot with network modelling, which I'll talk about in a few minutes. But ontologies, which are a class of taxonomy, and ontology is a taxonomy in which the interrelationships, the links between different nodes or aspects of a system are defined in one way or another, are a useful tool in managing uncertainty that's inherent in complex systems. So we can begin to classify the types of uncertainty that pertains in our modelling exercise. And uncertainty arises in modelling primarily across two types. One is uncertainty associated with randomness, a randomness of events that happen in real life. The stochastic nature of the solar and wind resource, for example. The randomness or stochastic nature of wholesale fuel prices in a day-ahead market or a half-hour market or an ancillary services market. The stochasticity that pertains to the frequency of voltage fluctuations on a power grid, for example. And that's sometimes termed aleatory uncertainty, the uncertainty associated with stochasticity or randomness within the system. And we also have uncertainty that arises from a fundamental lack of knowledge about the system or the subsystems that comprise that system of systems. So it might be ignorance of what needs to be modelled. It might be unawareness or ignorance about the time step, the time resolution over which a system needs to be modelled if one is undertaking time series modelling, for example. It may be a lack of knowledge about those deterministic processes that I was alluding to before, and how the algorithms that we design to solve those deterministic problems, and our knowledge of those algorithms may be incomplete. And we can further taxonomize, classify the types of lack of knowledge within that particular taxonomic classification. And the last three are often termed, or have been termed, systemic uncertainty. And the first three have been termed reliability aspects of uncertainty. But we can see, at least for the first three, how those aspects of uncertainty can relate to, for example, the type of equipment we're measuring the system with. How accurate is one's pyranometer, solarimeter, or reference cell in terms of what we're trying to measure? Or it might be very difficult to measure in a complex system. Within a solar PV device, it might be quite difficult to measure the atomic level or the electronic structural processes that are happening within the material of a PV device. Or it might be that we haven't realized we have to measure them yet. So these taxonomies, these structures of knowledge that I'm alluding to, are very useful in modeling terms. So this is basically a hierarchical diagram which very simply taxonomizes the uncertainty that arises from variability, not lack of knowledge. So they can be uncertainty about environmental aspects such as renewable energy resources. They might be human factors, human-centric stochasticity related to when somebody switches on an appliance and consumes energy in different dwellings in a city district. It might be a technical surprise. It might be that we put in a gas boiler into our building, assuming, as is often happens in dynamic building energy modelling programs, that it's going to perform at a fixed efficiency of 92%. But when we actually measure it in practice, and it is a very tricky thing to measure, the dynamic efficiency of a gas boiler, because one's dealing with thermodynamic processes, heat transfer, it's very difficult. We've done it, and those boilers that we've measured have had a mean performance efficiency of 82, not 92, with a standard deviation of about 12 or 15% around the mean, typically a Gaussian distribution. One can further taxonomize those environmental characteristics, for example, in terms of the solar and wind resource. But I'm not going to do that to death. I'll refer you to that paper by Jan van Asselt from back in 2001, who explicates this taxonomy of uncertainty very effectively. So what this suggests is that we need an integrated research approach. We're trying to integrate economic, social and policy issues with science and technology issues. The holy grail is to have a happy band of social scientists and geographers and engineers and scientists working together, all speaking the same language and all working together at the same time and on the same problems. But I've never experienced that, and I don't think anybody else has experienced that. That's for a future date. And if we can get us all working together in an integrated, holistic modelling environment, that will be great. But I think that's a few years hence. So we do still tend to work in our silos and try and marry up the outcomes of our modelling in some form of output, whether it's a journal paper or a simulation set of outputs. But regardless, what we're trying to strive for is integrated simulation and modelling, which is designed to address specifically some of the uncertainties that I mentioned previously. So where we can get data, we'll adopt a data-driven approach. Where we can marry up data sets from multiple domains to create integrated models and to specify conjoint outcomes in terms of, for example, energy yield versus energy affordability in a community, we'll strive to do that. We tend to work from the bottom up as well as top down. We tend to work in terms of, for example, high temporal resolution where we feel, and a lot of this is guesswork, where we feel that is a requirement, and then perhaps degrade that, where we find that the sensitivities, when we're more aware of the sensitivities associated with a specific subsystem modelling problem. What are our outputs? Well, we're trying to produce new policy, investor, science and technology, stakeholder knowledge. We're not trying to publish loads of papers and get them into the academic fraternity to improve our citation indices necessarily. Yes, we do, of course, because we're academics. But that's not necessarily the prime outputs of our work. We're trying to instigate change. So if, for example, that gas boiler is operating at a suboptimal efficiency because the M&E or commissioning engineer hasn't had the right training, and that can be a valid outcome of the modelling, then we must address that specific aspect via regulations and training, for example. And that's really what the key underlying cause of that is. It's M&E's ramping up the heat to pasteurize Legionella, an unexpected outcome, because they're so risk averse. They don't need to do that. The boiler's never in condensing mode. So we're trying to inform stakeholders, improve capability, produce roadmaps for business policy and technical stakeholders. We're trying to brief and we're trying to instigate useful change across the whole system, not just publish papers. I'm now going to talk at the last 15 minutes or so. I was hoping to leave a few more minutes at the end than I obviously am going to, but I want to illustrate this via a specific case study. This is a case study that my group, together with Ralph Gottschall's group at Loughborough, together with the Centre for it's not the Centre for Environmental Markets, the Centre for Environmental Policy at Imperial College. Some of you might have heard of Adam Hawkes, who was previously from Melbourne, I think. Maybe Sydney, I can't remember. He's at Imperial working with Bikash Pal and Chiara Candelise, who are co-investigators on this project. So, some of the key technology questions. How do we quantify PV performance appropriately, and what are some of the difficulties we're trying to overcome? Where should we locate PV at both small and large scale? How well does this system perform at large and small scales? How can we predict more effectively what the output of a particular PV installation might be, or set of installations? What are the distribution network and transmission network impacts of large-scale PV? And now we've got 10 gigawatts plus of PV, and it's still increasing. PV is still being installed despite the feed-in tariff largely being expunged. Some cost reductions have still been wrung out of the market, as often happens when you remove a subsidy from a marketplace. And we also have some of the more socio-economic questions side of things to answer, which is where I'm most involved in. So I'm going to be a little bit on shaky ground when I present some of the technical data here, but I'll try my best. Such as, what are our returns going to be on these systems? What are the actual emissions? I alluded to life cycle analysis and life cycle emissions. PV, as Muriel, you've done some work in LCA previously. PV, like every other technology, has an embodied carbon aspect to it. And they also have consequential carbon emissions in terms of what putting PV into a system means with regards to the incumbent or legacy plant that's also within that system. Obviously, and I know that Ian's team in SEAM have been working on this with regards to the impact of increasing levels of stochastic generation on what happens with the duty cycling of thermal plant, for example. Fuel affordability, look, all energy policies national energy policies that I'm aware of have the three key aspects of security of supply, environmental impact and affordability. But this third aspect of energy policy is often neglected. In the UK, there's a key focus on fuel poverty, and has been now for some years, since Brenda Boardman 15, 20 years ago defined fuel poverty as being a household that spends more than 10% of its net income on fuel to heat and power that household. In Eastern Europe, in the Baltic states, I'm aware of data that shows that sometimes more than 50% of household net income is spent on fuel for heating and power the household. So it is a key, really key consideration, which has been given relatively short thrift and little attention in the integrated modelling fraternity. More of that in a few minutes. So, very quickly, Dan Palmer, who's our GIS, or one of our GIS and PV system modelling experts, has worked towards putting together a process for predicting solar array output. It involves interpolation, kriging, named after, I believe, a South African precious metal prospector. Kriging, a process of interpolation using Met Office. There are 80 Met Office stations in the UK. We're quite blessed with Met Office stations that have pyranometer data, solar radiance data, temperature data, wind speed, etc. And that's all open access for the academic community. We can infer tilt and azimuth using LiDAR data from building surveys. Diane separates, and this is probably a fairly straightforward process to some of you in the room who I know have been working on similar techniques. We separate out beam and diffuse irradiation in order to translate the irradiation onto a tilted plane. We calculate module temperature from the Met Office temperature measurements. How accurate that is, I'm not going to go into too much depth here, but you can refer to the publications for that. And therefore we can compute the power output from the electrical model used. So, a little graphical process. There are 80 stations across the UK generating a dynamic UK-wide map, currently using historical data, but there's no reason this can't be done in real time in order to more accurately predict PV farm and domestic scale or small scale PV output. We use the building models and LiDAR data to create the in-plane irradiance. BRL model, I think people in the room will be more familiar about that than I am. Use the BRL model to separate and then translate using Hay and Mackay. I'm presuming people may be more familiar with Hay and Mackay's models than I am. And therefore calculate plane of array irradiance and then the output. Now if I'm very lucky, the movie will work here at this juncture. Oh, it does. Wonder of wonders. So this is one of the dynamic solar maps that Diane's produced for summer solstice, June the 21st in the Northern Hemisphere. And you can see the impact on weather fronts moving across the UK on that particular day from using Diane's simulation or movie. So, we use this approach to predict output from UK solar farms. We find that there are geographical differences, as you would expect. Not much surprise about the southern UK being more productive in energy terms than the north. We find that our installations rarely reach nameplate capacity. Obviously, that's an attribute of the environmental conditions that pertain in this particular location, and also that the maximum output does have a geographical difference. So for example, you can see the plot in the middle shows the difference in kilowatt hour per kilowatt peak, the specific output of solar farms in different regions. The yellow line, East Midlands, which is, if I can just point it out here, versus South Wales, which is down here. You can see the distribution of output is, as one would expect, higher in the south. But what's interesting about this is for the first time, it's calculated solar farm output which is specific to each substation. This is probably 132 kilovolt substation area. And in energy terms, we can predict for each DNO specific market area what the energy output from PV will be, and that's specifically for large-scale solar farms. Now, mindful of the time, this is the last section of the talk. I mentioned analysis under uncertainty and probabilistic techniques. One of the probabilistic techniques that we utilize is Bayesian network analysis or Bayesian modeling. And basically, it says that the Bayes theorem says that if you know something about the probabilistic relationship of a prior event, then one can infer something about a posterior event that will happen in the future. And likewise, one can work in the reverse sense, is that if you know something that's happened now, if you know enough about the relationships of the system of systems that alludes to, we can infer what the causes of that current output, that current aspect have been. So, for example, I alluded to earlier the situation of underperforming gas boilers. One of the things that you can do is infer that that actually was the result of suboptimal training for commissioning engineers. All it takes is for them to program in the right Legionella pasteurization program, and those boilers will, in all probability, work in condensing mode. So one can infer the cause of an outcome as well as infer an outcome from specific causes. And so a Bayesian distribution, a posterior distribution, the black line, is basically an aggregation of prior distributions of potential causal factors which can be ranked and scaled according to one's knowledge, the state of one's knowledge about those causal factors. So what we use are directed acyclic Bayesian graphs. Now on the right there you can see in the center a representation of an acyclic. Acyclic means that you can't go back the same way as you came. You cascade from the top generally down towards the bottom of the graph. Each of those ovals is a node, and behind each of those nodes is what's called a conditional probability table. It defines the probabilities of an outcome occurring at that particular node based on something else occurring higher up the node. And as you change the probabilities in the higher nodes, the daughter node, the outcome, the posterior associated with those two prior nodes, changes. So it helps us factorize multidimensional or multiparametric joint probabilities for complex problem domains. We're not necessarily deterministically measuring the outcomes, but one can use deterministic approaches to calculate the probability distributions in each node, as I'll show in a minute. And as I said, we can view new posterior distributions or we can prognose or diagnose. Prognose, tell the future. Diagnose, evaluate the past in terms of a present outcome. The key challenges for us in this are to gather enough multi-domain quantitative data to populate our conditional probability tables and to actually know what the causal links between different nodes are. But I could go around this room today, right now, if we had the time and the inclination to do so, and we could create a probably quite robust causal map about PV device subsystems on the one hand, or PV system applied, the PV system of systems on the other, i.e. the causal factors that relate to an outcome in either the applied PV domain or the PV device domain. And a challenge is to accommodate different temporal scales. So we set ourselves the challenge to calculate probabilistically the self-consumption profiles of a set of different domestic properties. And this graph just shows what happens if you use a relatively coarse time step of 1 hour versus a relatively fine time step, and it probably isn't fine enough to do what we would really like to do with regards power flow at the point of connection, because power flow is metered at millisecond levels, not at 1 second levels. So it shows that unless one adopts the right temporal, for example, temporal resolution when one is carrying out one's analysis, problems can arise. And the confidence that one has in an outcome would degrade accordingly. So what we've done there is we've run the previous time series that I showed was an output from a stochastic dynamic load generation profile program. What we wanted to do was for a community of, say, 1,000 dwellings, take into account the stochasticity of demand in terms of self-consumption. So what that graph shows are The bands, which are an allegory for probability distribution, for self-consumption as a function of the overall consumption of electricity per annum, as well as the size of the PV array. So the coloured bands illustrate the impact of different array outputs on self-consumption. And what this shows is that different occupancy archetypes, i.e. when the property is lived in or is occupied, has a significant impact on self-consumption levels. This is important in terms of feed-in tariffs, for example, because the UK feed-in tariff was implemented with a very simplistic assumption that export was 50% of PV generation across the board, unless one wanted to spend hundreds of pounds in installing a PV self-consumption meter. We use ontologies. This is a relationship diagram view of the Bayesian network, the sub-network for deriving self-consumption. We translate that ontology or entity relationship diagram into a Bayesian network. I haven't got time or the inclination here to go into detail in what each of those nodes are, but this is a representation of each node populated with its probability distribution. And these are output or posterior distributions for self-consumption, PV yield, gas consumption and electricity consumption for a specific geographical area for a city in the UK, Newcastle. We can also calculate financial aspects or economic aspects of the system, in this case a discounted cash flow analysis to derive net present value. And we can look at the net present values of different, or the returns on investment or techno-economic aspects related to different locations, 3 different locations, and the impact of different generation tariffs in terms of feed-in tariff policy development for those 3 different tariffs and 3 different locations. And by fixing a particular input parameter, such as a tariff or a self-consumption value, we can zone in terms of geography or policy scenarios or hurdle rates, etc. And finally, fuel affordability. I alluded to fuel poverty. We're fortunate in the UK to have a large data set of domestic gas and electricity consumption values. We also have very good census data, which allows us to use an approach called iterative proportional fitting to estimate household income across a specific geographical area. We call them LSOAs. These are local council areas typically comprising 500 dwellings. So we can estimate or predict the impact of low carbon interventions. Now that might be PV, this current work is around PV, but it might also be solar thermal, it might be heat pumps, it might be external wall insulation, loft insulation, double glazing, new gas boilers. Once you have the data, and as always data is king, one can add another subsystem to the Bayesian network model and compare the conjoint combined impacts or the individual impacts of different technology interventions. So we can, for example, using proportional iterative fitting as the technique, which has been adopted by a number of social scientist colleagues that have been involved in this work. We can predict the distribution of gas consumption, for example, by different building type, and we can predict by combining electricity consumption, gas consumption as the overall energy consumption and cost for a dwelling. With the PV generation and self-consumption, we can predict the impact on fuel poverty for specific geographical areas for those households without PV in comparison with those households if they are fitted with photovoltaics. And that, for policymakers, is a significant difference. That corresponds to an inferred or predictive reduction for this particular geographical area of fuel poverty of 21% down to 15.5% or 16%, which for policymakers is a very, very significant difference. I'm not going to talk about that slide because I'm running out of time. Maybe just finish by talking about new research Whether we're part of the European Union or not after next week's referendum, we hopefully will be involved in this project. It's a project which tries to build upon exemplar national projects across the 8 or 9 research partners in the consortium. We're trying to integrate these across different domains within an information infrastructure which will allow us to produce multi-domain predictions with regards to the impacts of specific energy system evolutions to a higher degree of accuracy than we've currently been able to do. So, for example, DTU in Denmark, that's Henrik Madsen, is an expert. His group is an expert in stochastic dynamic programming, which will allow us to generate in our particular work package the probability distributions for inclusion in those Bayesian networks that I alluded to before. So, in summary, holistic approaches and appropriate handling of uncertainty can add significant value when modelling or simulating multi-domain problems which integrate, for example, social, technical, economic, political and environmental aspects. Data, I'm probably preaching to the converted here, but data is king. The more integrated data sets we can utilise in an appropriate manner, the more we'll be able to improve the confidence of our predictions. And finally, we're aiming for impacts that will have resonance and will result in positive change across a wide range of stakeholder groups, whether they're working in the political space, technical, investment, or socioeconomic space. 2 minutes for questions.
Thank you.
Thank you.
It's hugely interesting, and I can see links to the sort of work that Anna and Jessie are doing on our PV map, for instance, which is live data, and you've got simulated data.
Mm-hmm.
And I'd love to be able to see what we can do with the different data sets, and we have nothing like the level of data that you've got on almost anything in Australia compared to what you seem to have. So that would be really interesting for us to know what we don't know in terms of data and what we should know.
But to that, I mean, I have been talking to some of the researchers who've been involved in that work, and we've got actually just as much to learn from you. So the objective there would be to, and we talked about, potentially joint publications and such, like joint work moving forward. It would be really interesting to map where each side can add value to have to produce a greater whole rather than lesser sum of the parts.
Yeah. Have we got questions? Yep.
Yes, thank you very much, Paul. Very interesting indeed. This variability analysis and the Bayesian approach seems very powerful indeed. One of the things that would be very valuable is you mentioned that you can use several different inputs to the model. Say you use the example of PV, but you can also use other things like insulation or something like that.
Correct.
So you could use this Bayesian model such as this to compare the relative impacts of these different.
That's the intention, yes. That's what we're currently embarking on, yeah.
Because that's something that's often very missing, completely missing. There's an advantage in having some mechanism like this, but it's very difficult to work out which is better or what the combination of different measures would be.
Yes.
And this allows an actual economic calculation and a society
Carbon calculation
and on several different levels, I guess, to work
Indeed.
out within the relative variabilities involved.
Indeed. And that has relevance to building regulation evolution moving forward. Unless we actually move towards a building in use performance aspect to building certification, then we'll never really solve this building energy performance gap that is tenaciously holding sway, in that we build buildings, we predict their energy performance, but when we actually measure the odd building here and there, more often than not they can be 100, sometimes up to 300% more energy intensive than they were designed and certified to be. And so to have more knowledge about predicting what energy performance of systems such as buildings will be, or retrofitting, in the retrofit context, what the potential impacts of different renewable energy microgeneration technologies or energy efficiency measures might be for different, different occupancy context, different building archetypes is the aim. And we're not the only ones addressing that. Rishi Chowdhury's group at Cambridge is also working in that space as well. There are a couple of groups in the UK and others around the world who have that goal in mind, Gavin, yeah.
Other questions? Oh, yeah.
I guess, thank you, Paul. So you had a slide there saying our results, actually the idea is to go to policymakers, to business. How effective in the UK, or in your experience, is that?
One hopes that by osmosis, or that something drips through. David Green, some of you may remember David Green from when he was CEO of the Clean Energy Council. He now chairs PRASEG, which is the Parliamentary Advisory Group in the UK, and we're a member of that. So one of the ways in which we try and influence policymakers is through the technical policy interface mechanisms that currently exist, and the Parliamentary Advisory Group is one of those. But also politicians are very, very swayed by vested interests, by the large corporates, and that won't change anytime soon. And so one can indirectly, hopefully, influence policymakers by making those key interests aware of one's results, especially in the context of investment risk. Those distributions that I was showing are meat and drink. These are what investment analysts and risk analysts use every day of the week in their work. So when you say there's a mean return investment predicted of 5.3% with a sigma around the mean of 1%, they know exactly what you're talking about. So trying to get these results into the investment community, and when one runs workshops with those stakeholders, Bristol City Council is one we're working with, some of the outcomes that we weren't aware of before are quite interesting. They wanted to work with us because it could shave off potentially a few percentage points in the amount of cash that they try and borrow by demonstrating that they're carrying out due diligence with Loughborough University. I thought, that's an interesting one. It's quite a big cross to bear, but we'll try our best. So there are ways and means, hopefully, of getting through to the politicians.
One side issue, you mentioned in passing the coal-fired power station that's converting to pellets, and who bears the carbon liability.
Yeah.
We, I guess, from Australia's point of view, try to put the carbon liability for all the coal we export onto the end-use country. And I don't know what the right answer is, but you're sort of looking at it from both points of view, and it's an interesting discussion.
I think that's an incredibly risky investment. It's a strategic power station. It's 8% of the UK's electricity is produced from that one power station. So it would be a really dangerous precedent if it were to shut up shop. But can you imagine the United States when they get really serious about Paris and national carbon budgets? Do you really think they're going to hold that carbon liability on their books? Because this is what we're talking about. We're talking about carbon accounting here. Are they going to be happy with that carbon liability remaining on their carbon balance sheet? No, they're going to push that back through to the UK, which will then draw into question, well, why have they been given a contract for difference with a strike price of 20 Aussie cents per kilowatt hour? Because that strike price was predicated on that being zero emission, a renewable energy. So it has cascading risks right throughout the policy and legal landscape, which could arise from that one decision. Maybe it's a good thing that it brings it to a head. I think it does, because there are severe problems, and have been for some time now, with regards biomass feedstock supply chains.
Been lucky, I guess, that there aren't lectures following us, are there? So no one's lining up out here. Have you got a lecture on in here? No. No, haven't. They just want to use the room.
I've got a follow-on point on that, the co-firing of tracks. There are power stations in Australia which are experimenting in co-firing as well. A can't quite remember which now, but they do use significant amounts, 20% I think of biomass sometimes in some of these, and so from a reduction in greenhouse gas point of view, it's got to be a good thing. I think here it's different to the situation there where it's a case of trading carbon emissions because it's all within Australia. So that presumably doesn't apply.
Drax isn't co-firing, they're fully 100% firing. So they've got 6 modules at 500 megawatts each. 3 of those modules are on pulverised coal, 3 are on wood pellets. The distribution of embodied carbon in wood pellets is really a tricky one. And some researchers are saying that the carbon emissions are accruing from the highly processed pellets that are being, and you've also got to think about the forest management aspects of it as well. Maybe at the upper quartile, maybe higher than burning coal itself. So you've got to think, what's that all about? I think the mean is about 200 grams per kilowatt hour. And coal at the moment in the UK is about 800 grams at the point of generation.
One factor, of course, is the amount of energy output is significantly lower for biomass than for coal. So that's probably one of the reasons that calculation, the higher end anyway, can possibly show.
But that technical decision to convert was predicated on the political decision to offer contracts for difference with a strike price appropriate. Yeah.
Okay. Probably people need to go, but thank you very much. That was very interesting. We hope to keep working with Paul after the meeting.
Thank you.